Looking at another function found in example 2.6 in section 1.2, let's find the limit as x approaches 0 of sine x over x. Again, to do that, we don't have a lot of techniques learned yet. One of the techniques is if you're given the graph already, like over here, because I'm given the graph already of sine x over x, we notice that as x approaches 0 from the left and the right, what are the function values approaching? They are approaching from the left and the right the value 1. Although the f at 0, sine 0 over 0 is undefined. Undefined because we cannot divide by 0. But the limit, the neighbors are fine. What is the limit of the neighbors? 1. Moreover, I can even do it now numerically. How do I do it numerically? Using a table. Sine x over x. As x approaches 0 from the left, like minus 0.1, minus 0.01, minus 0.001, minus 0.001, minus 0.00001, and we take them on the calculator to sine x over x. Simple, yani. It's not, we're not doing anything extra. So we do minus 0.1 radians, of course, your calculator, over minus 0.1. We get 0.998334. Try the next one, you will get this. Then the next, you will get this. Then 999999983, and so on. Here it's 0.9999. I don't know how many nines, and 83 in the end. Do you notice what are, as I approach 0 but smaller than 0, so from the left, the function sine x over x, its limit is approaching 1. Now if I do exactly the same thing for this from the right, meaning 0.1 to 0.01, 0.001, 0.0001, and 0.00001. Now since sine x over x, if I put a negative number in it, it will be the same value. So those two will have exactly the same value. So I'm not going to copy them, just not to waste time. You will notice that you will get the same answers here. Because if I have sine minus x over minus x, so the angle, I changed it from positive to negative. According to inverse angles for trigonometry, this will become minus sine x over minus x. The minus and the minus will cancel. So I'm left with sine x over x. So sine minus 0.1 over minus 0.1 is the same as sine 0.1 over 0.1. So we'll get exactly the same answers in this table, which means that the limit from the right is again equal to how much? 1. When the left and the right limits are equal to each other, we say the limit at 0 in general is equal to 1. This is another example of how to use graphs and how to use tables in order to find limits for functions. Now for some functions, look at this. The limit of absolute value of, x over absolute value of x. This is example 2.7. The limit as x approaches 0 of x over absolute value of x. What does it mean to have an absolute value of x? See, we have to be very careful when we do absolute value of x. I want you to realize what the meaning of absolute value of x is before I start solving this problem. Absolute value of x is a function which you input a number in. If the number is already positive, it stays the same, right? So absolute value of 2 is 2, absolute value of 5 is 5, absolute value of 7 is 7. So if a value is already positive, it stays the same. If a number is negative, like if you do absolute value of minus 2, what should you do when you have an absolute value? It should change to positive. How do you change a negative number into a positive number? You multiply it by a minus sign. So if the number is negative already, you multiply it by a minus sign again, it becomes positive. If a number is positive already, it stays the same. So absolute value of minus 2, since minus 2 is negative, it becomes minus 2 plus 2. Absolute value of 10 10 is positive, is 10. It stays the same. Similar, this is, be careful. If it was, for example, x plus 5, many students write it exactly the same way. It's not the case. If you have absolute value of x plus 5, you have to say, if x plus 5 as a total, yani all of it, you deal with it as one package inside the absolute value. If all the package is positive already, if all the package is positive already, it has to stay the same as the original package. Not x has to be positive. No, the package all inside the absolute value needs to be tested whether it's positive or negative. So if it was positive already, it stays the same. If it was negative all together as a package, what shall we do to that package? We shall multiply it by a minus sign. Haida on the side, other than talking about this example, on the side talking about absolute values, because I really want you to be proficient with absolute values. So this means that absolute value of x plus 5, if I want to really understand what it is minus x plus 5 if x is less than minus 5. It is x plus 5 if x is greater than or equal to minus 5, not 0. So students at many times mistake and keep it exactly the same even when the absolute value of not x, of something more complicated is inside the absolute value. So that's why now, what will we have here? If I want to study the limit around 0, there are two, of course, neighbors of zeros. 0 from the left and 0 from the right. See, when I'm at the limit of 0 from the left, what will happen? The values that I'm choosing will be less than 0, like minus 0.1, minus 0.01, minus 0.001, and so on. What will happen here when they are negative? The absolute value of x for values of x that are negative will be minus x. So if you want to simplify this, this will be x over minus x. And the x will cancel because we're not at 0. We're close to 0, but we're not at 0. So what will the answer be? You can try it out. It will be minus 1 in all of these cases. So what's the limit from the left of f of x? Minus 1. Do you see? You can take those values and put them, of course, in the calculator. Use the absolute value key. Where's the absolute value key? The absolute value key. All right, and check in the table. But if you want a little bit of analysis, algebraic analysis, see, when we are less than 0, what did we say the function absolute value of x will be? It will be minus x. So x over minus x, the x and the x are the same and can be cancelled because x is not 0. So then what do we have as an answer all the time? It will be minus 1. Whereas when we approach 0 from the right, we are values bigger than 0. What will this look like? For when x is bigger than 0, absolute value of x is nothing but x. It stays the same because it was positive. The absolute value will not affected by anything. So what happens? The answer will be 1. So when you choose 0.1, 0.01, 0.001, the limit from the right will always be equal. You notice that they are all equal to the same number. So this means the limit from the right of the function is equal to 1. Since those two limits are not equal to each other, we say that the limit around 0 does not exist because the left limit is not equal to the right limit. So this is a very important thing when it comes to talking about absolute values and how we represent absolute values in the best possible way and how to understand it as a function rather than just by the simple meaning saying that, oh, the absolute value of a positive number is positive or the absolute value of a negative number is negative. No, as a function, this is what it means to have the absolute value function. If absolute value of x is equal to a piecewise function made of two branches, one branch when the inside is negative and one branch when the inside is positive. If the inside is already positive, it stays the same. If it's negative, then we have to multiply it by a minus sign again, so that the minus and the negative sign that is already there change the answer into a positive answer. There are so many exercises in the section that we're talking about. So there are so many exercises. There is suggested exercises on the Moodle page. You can go and check what exercises are suggested for you to solve, and you try to solve them all. It helps a lot. All right, I already solved a couple of examples from the graph. Now, for example, for this one, the question says you sketch the graph. So the graph is not given to you. It's a piecewise function made of a branch that is 2x if x is less than 2, and x squared if x is greater than or equal to 2. And then if I sketch it, I can represent it. I can find the limit graphically. This 2x is a straight line for x less than 2. For a straight line, we need to draw 2 points and join them. Here as x less than 2, at 2, it's 2 times 2, 4. But it's open because x has to be less than 2. It's not. And then at 0, it's 0. So I got 2 points like this. I join them. This is the first piece all the way up to 2. And then the second piece starts at x squared and goes at x equals to 2. 2 squared is 4, which closes this because it's less than or equal. It closes this hole. And then at 3, it would be 9, which is here. So we join with a parabola. All right, this is how it looks like. A straight line followed by a parabola. The question asks in part A, what's the limit as we approach 2 from the left? If you notice, as you approach 2 from the left, this is 2. As you approach 2 from the left, what are the function values approaching? This is 2. This is the barrier between the left and the right at 2. 2, I don't look at it. I look at the neighbors. The neighbors of 2. What are the function values corresponding to the neighbors of 2? Those. What's happening to them? They are approaching the number 4. What is the limit as we approach 2 from the right? As we approach 2 from the right, those are our neighbors from the right. They are approaching. I look at their function values as if I'm creating a table in my head. And I notice what are those function values approaching? They are approaching the number 4. See, this means that the limit as x approaches 2 in general, not from the left and the right, is also equal to 4. Now, what's the limit as we approach 1? This is 1 here. 1 doesn't cause a problem. 1, 2. This is the function value. As we approach 1 from the left and the right, what are the function values approaching? They are approaching 2. Limit as x approaches 3 of f of x. This is 3. What is the function value at 3? 3 squared, it's 9. As we approach 3 from the left and the right, what do you notice? The function values are approaching what value? This is 3. From the left we approach, it becomes approaching 9. From the right we approach, it also approaches 9. So we say that the limit here is equal to 9. Directly, one shot. Number 13 is the same. In numbers 26 to 29, they ask you to sketch a graph with the given properties. I get usually many questions about this. How will I know what the right graph is? This question has so many answers. Each one of you can draw whatever they want. And there are so many answers that are correct. That's why if you look at the solution manual, it's not the only right answer that you have. But you should satisfy those. So you should draw a function f of x that satisfies those. What does that mean? At -1, the function value is 2. So you have to have a closed circle. -1, 2. Here you should have a closed circle because this is the function value. When x is equal to 0, y is equal to -1. So another closed 0 at 0, -1. F at 1 is equal to 3. So another closed circle from 1 to 3. Limit as x approaches 1 does not exist. For a limit as x approaches 1 not to exist, what should happen? Either we should have a hole, which is not the case at 1 here we have a closed, not a hole. Either we should have a jump or we should have a vertical asymptote. A jump is very easy to control. What about the rest? How can I graph it? You graph it the way you want. You can graph it as a curve, you can graph it as a straight line, then as a straight line here. But then what do you have to guarantee? You got those correct already. Now you want to guarantee the limit does not exist. For this limit to not exist means the left should not behave like the right. These are the left neighbors at 1. The right neighbors should behave in a different way. So what will I do? I will make a jump and then I will make a curve. It could be a curve, it could be a straight line, it could be zigzag, it doesn't matter. So that's why the shape of the graph is different. But what did I guarantee? If I look at the graph I have over here, I can guarantee that f at -1 is 2, f at 0 is -1, f at 1 is 3, and I can guarantee that the limit at 1 does not exist. Why? Because the left neighbors are approaching 3, whereas the right neighbors are approaching 1. So I made the left neighbors not behave like the right neighbors, which means the limit does not exist. So these are the problems that you're responsible for in section 1.2. See, in section 1.2, we don't learn a lot of things. We just learn the concept of limits. We learn the idea of limits. What is limit? What are limits? Why are limits required? Why are they needed? What's the added value? How does calculus differ from pre-calculus and algebra? And how do we find limits algebraically? And how do we find limits numerically by using tables of values like the one we used before? So either graphically from the graph by studying the graph itself, or by studying tables of values. I want to again insist that those tables of values are just for you to understand what is a limit and what does a limit measure. But again, as I said before, these are primitive methods and we are never going to use them in any exam. It's just for you to understand that limits do not study values on their own, discrete values. It studies a pattern. How is the function behaving as we approach a number? That's what we study when we study limits, basically. All right.